So in our last part, we have discussed about GOC, General Organic Chemistry. Okay, and I've given you some introduction about GOC. That is, I've told you how organic chemistry originated. Then, apart from how organic chemistry originated, we have also done the catenation, isomerism, the reason for organic compounds to form so many different number of compounds or numerous compounds. So that also we have done in detail. Now after that, we have done isomerism also in detail. I've given you a list of carbons, like what is one carbon called as, two carbons called as, an IUPAC as well as common name. That list has also been done. A list of functional group has also been taught to you. So now what are we going to do in this part, in this section or part 3 of GOC, is quickly we'll go through the importance of organic chemistry. Okay, so talking about the importance of organic chemistry here, we are having, say for example, pharmaceutical, right? Pharmaceutical industries, here you require organic chemistry. Apart from that, right, medicines, you know how important medicines are to you. Then apart from that, in fuels, right? So let that be diesel, petrol. Diesel is, by the way, petrol is, by the way, octane. Okay, and waxes are about 20 carbons. That's ecocene. Beyond ecocene, they are waxes. Okay, then not only petrol, but your LPG or oil, petroleum jelly, or other petroleum products like wood polish also is coming under what? Organic. Then the dye industries. Okay, then polymers, like dye industries will be the pigments, they are coming under organic. Polymer chemistry, then uh, plastic, okay, this is also coming under organic. Cosmetics, then food industry and fertilizer industry, all this is coming under organic. Okay, so now I mean, this can just go on, this list can just go on. Organic compounds, we are surrounded with organic compounds, and we cannot, I cannot just end this list, it can just continue. Okay, so now you've understood the importance of organic chemistry. Okay, now let us move to a few more reasons of why we are having numerous compounds in organic chemistry. So first thing which we had discussed in the last class is high catenation ability. It can go on catenating, it can form carbon carbon bonds for a very long chain. Okay, then higher carbon carbon dissociation, bond dissociation energy. That means the carbon carbon bond is not very easy to break, it is difficult to break, which makes the chain long lasting, or you can say durable. Okay, then carbon is tetravalent, it's having valency 4, so that it can form 4 bonds from all 4 sides. Then compounds exhibit isomerism. This also we have discussed in detail, that these compounds are able to show isomerism. Because of isomerism, like the same compound butane can be converted into 2-methyl propane, something like this. Okay, with the 4 carbons only. Okay, I can get 2 compounds. With the 4 carbons, I can get 2 compounds. One is N-butane, straight chain butane, and the other one is 2-methyl propane. So with the same molecular formula, I get more number of compounds. So isomerism is also increasing the number of compounds. And carbon exhibiting bond multiplicity. That means the carbons can show a single bond, they can have a double bond and a triple bond as well. So single, double, and triple. So multiple bonds can be there in what? Carbon. Okay. Now moving on to the next point, to exhibit of tetravalency, carbon forms all 4 single bonds. You can form all 4 single bonds, 2 double bonds, 1 double bond, 2 single bonds, or 1 triple bond and 1 single bond. This is also possible in case of what? Carbon. Now have a look at this. All alkanes, like we have done in hydrocarbon, saturated, unsaturated. So we have done alkanes, alkenes, and alkynes. So talking about alkanes, all alkanes are sp3 hybridized carbons with a bond length of 1.54 angstrom. See, sp3 hybridized is a electron donating group, so it is not very electronegative, so the bond length is a little higher. Okay, the bonds don't hold each other very tightly, that's why the bond length is a little higher, 1.54 angstrom. The bond length between carbon and hydrogen is small, because hydrogen is a smaller atom. I hope you know what is the bond length, right? What is the bond length? Yeah, bond length is, like, say for example, we are having 2 districts, Pune and Solapur. So let's consider this to be Pune and this to be Solapur. So how do you measure the distance between Pune and Solapur? Do you consider this distance from here to here? Right? Do you consider this distance? No. Right? This will be too long. Do you consider, now here there is a district, okay, Temburni, Indapur. Okay, so do you consider this as the distance between Pune and Solapur? This will be just 20 kilometers. Here you are in Pune district. By the time you come here, you have entered Solapur district. So do you consider this as the uh, distance between Pune and Solapur? No. So if you want to consider the distance, you will see the GPO, General Post Office of Pune, and GPO of Solapur, which is generally in the center. Okay, and you'll measure this distance. So this distance is actually the, tell me, this distance is actually the actual distance between Pune and Solapur. Similarly, if you want to measure the distance between two atoms, so say for example, if this is a hydrogen atom, and if this is say for example, we'll take another hydrogen atom. So what are we going to do is we are going to take the centers of two atoms. Okay, we're going to take the center of two atoms, and the center of two atoms, we're going to measure the radii, or you can say the distance between the center of two atoms. This will be the bond length. Now this is hydrogen hydrogen bond length, and hydrogen hydrogen will be the smallest molecule which we have, right? And hydrogen are having us very small, because hydrogen is the smallest atom. So this radii and this radii will become what? The bond length. R plus R2R, this 2R is the bond length. So that is bond length. Then coming back to our PPT, now you can see the bond length between carbon hydrogen is a little smaller, because hydrogen is a small atom, and the bond length between carbon carbon is 1.54, and here it is 1.09 angstrom between carbon and hydrogen. The shape is tetrahedral with a bond angle of 109 degree 28 minutes. The bond angle remains 109 degree 28 minutes. With alkenes, we are having sp2 hybridized carbon with bond length, you can see a little smaller, because here you're going to have double bonds, and double bonds decrease the bond length to 1.34. Then we are having a bond length of 1.08 angstrom between carbon and hydrogen. The shape is trigonal planar with bond angle of 120 degree. Then alkyne is sp hybridized with bond length of 1.20, and you can see that the bond length is further decreased, because one thing is very clear, that bond length, okay, or you can say bond strength, is inversely proportional to bond length. So greater the bond strength increases, smaller will be the bond length. And what we can say is bond strength is inversely proportional to bond length, and also the number of bonds. Okay, if you are having a single bond, the bond strength will be low. It's directly proportional. If you're having double bond, the bond strength will be even higher. And if you're having a triple bond, the bond strength will be even more higher, which will decrease the bond length. And that is very visible over here, right? You can see single bond is having, carbon single bond is having 1.54, then carbon double bond is having 1.34, and carbon triple bond is having 1.20 angstrom, right? So this is the alkynes will have a linear geometry, right? Linear geometry with a bond angle of 180 degree. Okay, so even in your single and double bonds, now have a look what is happening over here. Like say for example, you are having single bonds, right? Single bond is, I told you, it is sp3 hybridized, and it is formed by overlap of SS, that is in case of, that was in case of hydrogen. Okay, SS overlap, hydrogen and hydrogen. In between carbon and hydrogen, we'll have sp overlap. Okay, p orbital and s orbital overlap. This is called as the sp overlap. Then in between carbon, this will form a sigma bond, this will also form a sigma bond. Then in between carbon and carbon, we may have the pp overlap, right? This pp overlap will give you, this pp overlap will give you again a sigma bond with a single bond, right? It will be single carbon, single bond carbon. This was carbon single bond hydrogen, this was hydrogen single bond hydrogen. And we can also, if you want to form a double bond, then we'll be having a p pi overlap. Now what is a p pi overlap? Have a look. This is a p pi overlap. So in order to form a double bond, like in a double bond, you will have one bond will be your pi bond, and the other bond will be a sigma bond. So the sigma bond is either formed by an ss overlap, sp overlap, or a pp overlap. But a double bond is always formed by the lateral overlap of the p orbitals, that is p pi overlap. And so what about a triple bond? In a triple bond, your sigma bond, which is in the center, is sandwiched between two pi bonds, right? It is sandwiched between two pi bonds. So sigma bond is sandwiched between two pi bonds. Okay, so in triple bond there are two pi bonds and one sigma bond. Okay, let's jump back to the PPT. Yeah, so that's how the sigma and pi bonds are formed. The next topic is about the primary, secondary, and tertiary carbons. So here we are having, say for example, this structure, and we need to identify which one of the carbons is secondary, tertiary, and quaternary. So pay attention towards this bond. This carbon is being attached to how many other carbons? Like this carbon is directly attached only to one carbon. This carbon is directly attached only to one carbon, so it is a primary carbon. Then if you're talking about this carbon is directly attached to 1, 2, and 3 other carbons, since it is a tertiary carbon, right? And this carbon is in turn being attached to two carbons, since it is a secondary carbon. And this carbon, you can clearly see that it is attached to 1, 2, 3, 4 carbons, since it is a quaternary carbon. Okay, so primary, secondary, tertiary, and quaternary, and obviously these are all primary carbons because they are attached only to one other carbon. So primary, secondary, tertiary, and quaternary. Now in our next part, what are we going to do is we are going to see the nomenclature, details of nomenclature, IUPAC nomenclature. So have a look at the IUPAC nomenclature in our following part in detail.